All right, so in yesterday's lesson, we talked about not a new type of bonding, but unequal sharing that results in what we call polar bonds. And polar bonds can result in polar molecules. And polar molecules have dipoles, and they're sticky. They can stick to each other. Depending on how big that delta En is, that determines how strong the dipole is. So notice here we have a polar molecule of water. The delta En is 1.28. That's quite strong. That's really sticky. Here we ended up with a polar molecule, and these bonds, they're not very sticky. Oh, but that one bond is quite sticky. It turns out that this is not as sticky as water because water has two OH bonds, making it really sticky. But it would be medium sticky. They would stick, but not quite as much. And these guys here that are nonpolar wouldn't be sticky at all, okay? And we can see here, we know that water is a liquid. And that's what molecules do when they're sticky. They clump together. And that's what a liquid is. It's a big clump of molecules sticking together. CO2 we know as carbon dioxide. That's a gas. It's nonpolar. They don't stick to each other at all. They don't interact. They can bump into each other, but they don't actually attract to each other, and therefore they move freely as a gas. Gas particles move freely on their way. That's why they can fill all the spaces of the room. And that's why water in a container cannot escape easily and fill all the spaces in the room. Why? Because they're all sticking together. They're sticking to each other in here. All right? And that's what we want to talk about today. Today we want to talk about the forces that hold other molecules together. And that's what results in our physical states. That's what we can then perceive as being solid, liquids, or gases. Let's define these two terms that we've got here. And the first term I want to define is an intramolecular force or bond. We are using the term forces here, but really you can interchange the word force and bond because really it's forces that create a bond. You could even take the term gravitational force, right, that holds us on the surface of the Earth, and you could call it a gravitational bond. We're bound to the Earth by gravity. You can't just get up and leave the Earth. Why? Because there's a bond between you and the Earth. It's a force. It's a force. So even though we're saying here an intramolecular force, we're really just talking about bonds. Now notice I've highlighted the term within. Inside a molecule, there are bonds that hold the atoms together. Single bonds, double bonds, polar covalent bonds, ionic bonds. We have learned about intramolecular forces. That's what we've just finished. The bonds within a substance, a molecule. So for water, those polar single bonds, those are the intramolecular forces. Okay? And we've dealt with that. That's really not what this lesson today is about. We know about the bonds between ions and atoms in an ionic compound or a molecule. What we want to really talk about today is intermolecular forces. The prefix inter means in between. So what we want to talk about today briefly is what holds molecules together. Not what holds them together within themselves, but what holds adjacent molecules together. And really, it comes down to how sticky are they. I use the term stickiness because it is a good term. When two things are stuck together, it means you can't pull them apart easily. When two water molecules get together, they're attracted to each other. They're stuck. Even actual sticky things that we encounter have strong intermolecular forces. That's the whole drive of this company 3M that comes out with a new sticky something every 2 months, it seems. Post-it notes. Something that's a little sticky, but not too sticky. We all know the way Post-it notes work, right? Take off a Post-it note. It's a little sticky. The pad of paper doesn't disappear, but you can stick that to something. Right there must be some intermolecular forces that are attracting between the sticky molecules created by 3M and my thumb. It's sticking together. Actual stickiness can be explained this way as well. There has to be something that is applying a force of attraction between the paper and my thumb. So using the term sticky is the right term. It is the term we want to use. Looking at the prefix, inter means between, in between adjacent things. If you want to go to Florida, you need to take a highway that brings you from one state to the next state to the next state. What do they call those highways? The interstate. It means it goes between states. If you have a computer here and you want to talk to another computer, not like within our school, that's within, but I want to talk to another computer that's maybe at the ROM in Toronto or perhaps the Smithsonian or with Mr. Facebook. I don't even know what that guy's name is anymore. Anyway, what do you use to communicate with computers way out there? The internet, right? If I want to talk about communicating with a computer within this building, and we do it all the time. Right now I'm running PowerPoint, and that PowerPoint is not installed on this computer, but it's installed on a server somewhere in the school. I know where it is. Doesn't matter. It's another big computer somewhere in the school. I don't have to go all the way out into the internet, but what I use is what is called the intranet. It's an actual term. If you've taken computers, you've learned about it. The intranet is within your own computer network. This is our interface for the intranet. It gets us to different programs that are existing within our computer network. If I want to talk with another computer outside of the network, I need to run, where is it? I could run that one, but it's painfully slow. I never use that one, but I could use that one, which I use, Firefox, right? So if I want to access the internet, I do that. Okay, so intra means within, and inter means in between adjacent things. And that's what we want to look at. A little diagram here, and you know what? I'll draw this for you on the board. I do want you to draw it, but I'll draw it for you on the board. And actually, we're not going to use water molecules. Let's use something even simpler. Let's draw an H and a Cl. So please draw that underneath. And I'm going to put an H and a Cl here, just beside it. And we already know that this is a polar bond. One of these ends is slightly negative and one end is slightly positive. Please recall or flip back into your notes which is which. Or just check the delta, or just check the electronegativities. Which one has the high electronegativity? Dallas? Chlorine. So what does it get? Slightly negative, slightly positive, slightly positive, slightly negative. And just like a couple of magnets nearby, there's going to be a force of attraction between those two things. That's simple. That dashed line represents an intermolecular intermolecular force or bond. All right? Intermolecular forces are always relatively weak compared to an intramolecular force. They're strong. When water is boiled, I'll wait for you to write that down. I'm getting excited. When water is boiled, let's say that this is liquid water, and the water is a liquid because all of the other water molecules are sticky towards the other molecules. When water is boiled, do you still have H2O when you're done boiling water? Physical change? Physical change. Do you still have H2O? Yeah, the molecule doesn't change. Which means when water is boiled, it is these connections that are holding the water as a liquid that are broken that allows the water molecules to go free. If the bonds inside an atom were weakest and this was strong, which would break first if it was the other way around? The intra would, but that's not what happens. When you boil something, the inter breaks first, which means it must be weaker, because the weakest thing is what breaks. Every time, everywhere. If something is broken that you own, whether it is a lawnmower or an iPod or whatever's broke was the weakest part. That's always the case. That's what defines it as being weak. It breaks first. Okay, let's talk about types of intermolecular forces. First, ion-ion forces. We've already encountered these. Because remember, ionic compounds are really just an extension of an unequal sharing. If I'm ranking intermolecular forces, these are the strongest. Because they're held together by full-on charges. None of these little delta negatives and delta positives, not in an ionic compound. Complete transfer, which means they're super sticky. Which is why you can't take a piece of salt and squish it in between your thumb and your finger. Because the bonds in your thumb and your finger are actually weaker than the bonds in the salt. So when you try to squish the salt in your thumb and your finger, your skin bends first, because it's the weakest. If you want to draw a little representation of this, we've already done this, just simply do a little Na plus, Cl minus, Na plus, Cl minus, Cl minus, Na plus, Cl minus, Na plus, and if you really want a third row, go for it. We've looked at ionic compounds. They're held together strongly. Okay? So each adjacent NaCl is being held together by a strong, full charge. Makes it strong. Let's now move our way down to weaker intermolecular forces. Are we good for writing? Next, I just put the strongest. Strong and directional, that's good. Don't worry about the directional, we got the strongest. Next is what we call dipole-dipole forces. And again, I'm going to make you draw the H and the Cl. You can draw it exactly like we did, except without the definitions. It only makes sense to go from that full-on charge of an ion to the partial charge of a polar bond. And we call these dipole-dipole. And on your assignment and on tests, this is what you're going to be putting in that last box. I'm okay with dip-dip, because that's just fun to say, right? And every kid at some point in their life had their favorite dip-dip to, well, as you know, dip perhaps fries. Everybody's using the term dip-dip at some point. In this case, it means dipole-dipole interaction. One dipole is attracted to another dipole. They're not as strong, and they're not directional. It means that their direction can be in many different locations on the molecule. When you have directional forces, like this little tetrahedron that I built, it's fairly strong, all right? Now I can crush this with my hands because I have superpowers, right? And so I can overcome those. You might not be able to do it. Anyway, but they're fairly strong, right? I can flip that around a little bit and it holds its shape. That would represent an ionic situation. If I look at something here like this plasticine, and I've put a whole bunch of bearings in it, because this also has some bearings being held together by the strong directional pieces. They're being held together, like the bearings are still being held in a shape, but because the forces don't have a specific direction, it takes nothing for me to change that orientation of where the ball bearings are, because the forces aren't straight on and directional. They're kind of being held together by the plasticine. In terms of physical states, when we have substances that are locked into positions, what do we call that physical state when the molecules are locked into a spot? These are solids. When it comes to molecules that aren't locked into place, but they're not free to fly around like crazy, like let's not be crazy, they're not able to just take right off, like I can't just squeeze this and have a bearing, come popping out and hit me in the head, right? It means they're kind of held together, but they're able to kind of flow past each other. What physical state describes things like that? Liquid. That's exactly what's happening with our dipole-dipole interaction with this water. We've got some attraction holding it together, but they're not like locking it into place so it's able to kind of move freely. Okay? Now, dipole-dipole forces describe anything with a dipole. There's a very special type of dipole-dipole interaction that I'm going to put next that is actually a little stronger than just general dipole interactions, and it gets a special name. And that special name is hydrogen bonding, and you'll notice I haven't put another new number here, because hydrogen bonding is also an example of dipole-dipole interaction. It's just really strong. It's to the edge of being almost ionic. So this really still counts as a dipole interaction, but it turns out that when hydrogen atoms, because they have a delta E, an En of 2.2, are bonded to nitrogen, oxygen, or fluorine, and they are right in the upper highest values of electronegativity, fluorine being the highest. I think oxygen next and then nitrogen after that. When hydrogen bonds to it, we end up with those big delta ENs. Did I erase it, or where did my water molecule go? Water, 1.24. That's getting close to that 1.7 mark. And when they have such a large delta En, it means their dipole is really big, and it means that they're really, really sticky. On that worksheet, H bonding is going to be one of the choices that you're going to put as the intermolecular force. You need to look to see if in the molecule you have hydrogen bonded to either a nitrogen, oxygen, or a fluorine. And if you do, there's the ability for H bonding. It makes it sticky. Makes it really sticky. So these are so special that we give them their own name. And it's this hydrogen bonding that really allows liquid water to be a liquid. It's very important. In biology, you will talk about hydrogen bonding over and over again, especially in the grade 12 when you start doing biochemistry. Hydrogen bonding becomes a very important thing. Hydrogen bonding is what holds the two strands of DNA, well, I don't know what do you call it. DNA is a double helix, right? But what are the two individual strands called that are held together? What do they call that? Are they DNA strands, two DNA strands? And then you break it apart during mitosis and the new one is built on the side of it or something like that? I don't know. That's biology. I struggle with it. But DNA strands are held together by hydrogen bonding. All right? It's a very, very important type of structure. So we give it its own name. Okay? So in here, between the H and the O, we would actually have what we would call a hydrogen bond. All right? And now on to the last one. And this is the weakest intermolecular force. And I'm going to just let you write on this one, and then I'll describe it in a moment. There is another slide that has some more words for the description of London forces. I'll get to that in a moment. So you don't need to put the title down again. It's just a continuation of the London forces part of the note. What's dry ice? Does anybody know what dry ice is made up of? You've probably heard of dry ice, right? You can put dry ice into a fog machine and it'll create fog for effect. Halloween, right? That type of thing. Does anybody know what dry ice is made up of? Yep. No, it's not carbon monoxide, but you're close. Which is good because it'd kill you. Yep. It's carbon dioxide. It's carbon dioxide in a solid form. And dry ice has a temperature of about minus, I'm not 100% sure. Let's go with 70 or 80 degrees Celsius. I think it's down in that range. About minus 70 or 80 degrees Celsius. Quite cold. You wouldn't want to keep it on the palm of your hand for too long. You'd get frostbite. But that is solid carbon dioxide. And we've just learned earlier on in the class, what type of molecule is carbon dioxide? It's a nonpolar molecule. But somehow, at 70 minus 70, minus 80 degrees Celsius, carbon dioxide goes from being not sticky at all to being able to stick together in a solid crystal form, because that's what ice is. It's when molecules solidify. So if solid carbon dioxide can be made, then there must be a way to explain the stickiness of nonpolar molecules, because it exists. They have to be sticky at some point. That's what London forces does. London forces describes the stickiness of nonpolar molecules. Nonpolar molecules have no dipoles, so they're not strongly attracted to each other. They're not very sticky. That's why you've got to get the dry ice or the carbon dioxide so cold in order to make it solidify. However, there are very weak forces that exist between adjacent molecules. The outer electrons can be repelled to the other side of the molecule by the presence of another molecule. Let's write down the rest, and then we'll talk about how this particular, no need for a new title, they're just new bullets, how this particular process works. So on the last slide, the last comment was the electrons from one molecule can cause electrons from another molecule to be repelled away, can kind of push them to the other side. This results in what we call a short-lived weak dipole. This results in a very weak attraction between nonpolar molecules. The more electrons a compound has, the stronger this force is. Let me show you a picture to illustrate it. Let's say that we had some kind of molecule, a very simple atom. It might even be just, it might even be a neon atom, all right? It's got electrons around it, proton in the middle. If another neon atom were to come along and maybe bump into this side, what would happen is the electrons would be repelled to the other side of the atom, literally just repelling them away because two electrons will repel each other. What that does here is it creates a very small, so I'll try to draw it really small and I'll get a better color. It creates a very, very tiny delta negative on that side. Very tiny. Much smaller than any dipole that we have in our molecules. And a very tiny delta positive on that side. What can happen is when that gets close to another atom, it's going to repel those electrons to the other side very quickly, which then results in two of them that look exactly the same for a very brief moment in time. It's going to make a little tiny negative on that side, a little tiny positive on that side, and that's going to make a very weak force of attraction in between there. And it happens fleetingly. They come close. This process happens very quickly. It creates tiny little dipoles. They're attracted for a brief millisecond, would be way too long, right? We'll go with a nanosecond. And then the electrons return to their positions and the force is gone. But it happens all the time as the molecules get close to each other. So the closer they are, the more they can do this, and then they can get sticky. So the carbon dioxide, even though it's nonpolar, when they get cooled enough, they get close enough together, they can start doing this, and then they stick together a little bit. but it's a very, very weak force of attraction, and it doesn't take place very long. Notice in the last statement it says, the more electrons a compound has, the stronger it is, because the more electrons a compound has, the more those electrons can move to the other side. Plastics are made from non-polar molecules. These are non-polar. The only forces holding this plastic together is London forces. But plastic molecules are huge, and they have piles of electrons. And because they have so many electrons, they can stick together as a solid at room temperature. So London forces are weak, but you need some really big molecules in order to have a solid. Let's now summarize so we can just finish this here. So strong to weak, you can make a little table. I'm just going to list our different intermolecular forces here. And I'm going to put this right here in the middle. What was the strongest intermolecular force that we encountered? What's the stickiest interaction called? Yeah, Chelsea? Ion, ion. That means we stick an ion to an ion. Excellent. What's our next as we decrease in strength? What was the next one? Chris? Dipole-dipole, but there was a specific type of dipole-dipole that was stronger than just dipole in general. H bonding. Must have the hydrogen bonded to an oxygen, nitrogen, or fluorine in the molecule for that to happen. Then what's the weakest after that? Dip, dip. Dip, dip. And in the end, the weakest of them all, if there's no dipoles, London forces. London is named after the gentleman who proposed those forces first and calculated them out. All right? No big deal. Physical properties. What type of state are we typically going to find these ones that are really sticky? What physical state are we going to find them in? Yep, Janessa? Solids. This ranges then from solids down to, what film I'm going to put in the middle here? Yeah, Janessa? Liquids, liquids, and then gases. All right? And that's just a general thing. Like I said, plastics are only London forces, but their molecules are so big, it makes them a solid at room temperature. But for our starting into thinking about these intermolecular forces, that's a good start right there. Question? It depends. It's not that I was putting one with each. This isn't a memorized situation, but what I'm trying to say is, if the intermolecular force is strong, at room temperature, it'll likely exist as a solid. And if the intermolecular force is weak, it'll likely exist as a gas at room temperature. I'm not putting one with a particular one. All right? Any other questions? There's a little bit of homework to answer this. Right now, I am going to continue on with naming molecular substances, because this really wasn't a whole lot. But let me guide you to your little worksheet. Now you have the ability to do the complete worksheet, because that last column, you were to put in what the intermolecular force is. All right? Once you're finished describing what type of molecule it is, whether it's polar or non-polar or whatever, you can then say what kind of intermolecular force is holding it together. Now, one last thing that I did fail to mention, and it's quite important. All ionic substances and all molecules have electrons, which means everything else, ion-ion, H-bonding, dipole-dipole, also feel London forces. It's like London is there for everything, but when it comes to nonpolar, that's the only thing that holds them together. A dipole-dipole interaction will still have London forces, but the dipole-dipole interaction is stronger than the London, And so we usually just talk about the dipole-dipole. That's why down at the bottom of that particular page, you'll notice there are 2 marks for the intermolecular forces. And that's because all substances can feel the effects of London forces. All of them can. You catching what I'm pitching? And some others can have secondary effects. All right? Okay? Everything is being affected by London forces, but if it has a dipole, or if it's H bonding, or if it's ion-ion, there's a second effect as well. All right? Okay, so I'm going to stop this recording here for a moment. It's going to take a moment to